Okay, in this video we're ready to start section 4.5, which is on curve sketching. This is where we're going to put together all of what we've been building towards in 4.1 and 4.3 as we've learned about how the derivatives give us various bits of information about the graph of a function. So we're going to put it all together and we're going to get some information from the original function f. From f prime, of course, we'll find out when the function is increasing and decreasing and the location and value of the maxes and mins. And then from the second derivative, we'll get the intervals where it's concave up and down and the points of inflection. Okay. Now, we spent the last two sections really focusing on what the derivatives tell us. So I want to spend this video just reviewing the algebra and a little bit of calculus for what information we can get from f. Okay. So the first thing is the domain. Now, I might ask you explicitly, what is the domain of this function? I might not, but it's something that you always want to keep in mind. So, for example, if I were sketching f of x equals the square root of x, I know its domain is just everything from 0 to infinity, including 0. So, I want to make sure that I'm not graphing anything over here, but I am graphing stuff over here. And when I have a finite endpoint like that in my domain, if it's included, I do want to make sure that I include that starting point. Now here that starting point is at the origin, so it's very clear what its coordinates are. You want to make sure when a point is important like that, that it's clear exactly where it is. So if it's the origin, I can see that it's at the origin. Anywhere else you'd probably want to label the coordinates. Okay. Let's suppose I had a function like this. Let's suppose I had g of x equals x times the natural log of x. Now here, the domain is everything from 0 to infinity, except that 0 is not included because I can't take the natural log of 0. So that's not in the domain. I'm not going to have a point there. But I do want to know how my graph starts out. So when I have a finite endpoint to my domain, but it's not included in the domain, what I'm going to need to do is evaluate the appropriate limit. So I'm going to take the limit as x approaches 0. Now it's going to be a one-sided limit. We can only approach 0 from the right if we're in the domain of this function, because to the left of 0 we're outside of the domain, of x times the natural log of x. Now if I look at this, x is going off to 0. The natural log of x is going to negative infinity. Remember what the graph of the natural log function looks like is something like so. Okay. So I've got an indeterminate product, so for that I'm going to want to use L'Hopital's rule. Remember, I need to first of all rewrite this as an indeterminate quotient. So rather than multiplying these two things, I'm going to divide by one of the reciprocals. And I'd rather have the reciprocal of x than the reciprocal of the natural log of x. So I'm going to say this is natural log of x over 1 over x. So that's the limit as x goes to 0 from the right, the natural log of x over x to the negative 1. Okay. Now, if we've done this correctly, this is now an indeterminate quotient. So let's see, that's going to negative infinity. The reciprocal of x, when x is positive, is going off to positive infinity. So this is an indeterminate quotient. So I can apply L'Hopital's rule and say this is the limit as x goes to 0 from the right of the derivative of the natural log, which is just 1 over x, times the derivative of x to the negative 1, which is just negative 1 over x squared. Let's see, that's the limit as x goes to 0 from the right of 1 over x times negative x squared over 1. That's the limit as x goes to 0 from the right of negative x, which would just be 0. So that tells me that although there isn't a point at the origin, the graph of x ln x would have a hole at the origin. So that coming in from the right, we'd be expecting there to be a point there. Okay? And that's kind of interesting because seeing the natural log, I might have thought there was a vertical asymptote to start out with, but no, there's not. It turns out that there's just going to be a hole there. And so I would want to connect the rest of my graph to that once I figured out what the rest of it looked like. Okay. So you're always going to be keeping in mind what the domain is, and anytime you have a finite endpoint, whether it's included in the domain or not, you want to indicate the behavior of the function at that point if it's in the domain, or as it approaches that point if it's not. Okay. All right, intercepts. That's just where we cross the x and y axes. So if I wanted to find the y-intercept, well, if I'm on the y-axis, then I'm not to the left of it or to the right of it, so my x value is 0. Okay. So I'm going to have 0 and then just f of 0. Okay. Let's just do an example. Let's suppose I had f of x equals x squared plus 2x. So if I plug in 0, f of 0 is 0 squared plus 2 times 0. That's going to be 0. Okay. So the y-intercept is the origin. That's going to be 0, 0. Notice the y-intercept is a point. It's not a number. Okay. So if I explicitly ask you what is the intercept, don't tell me it's 0. That's the y value of the intercept. The intercept is the point 0, 0. Okay. And then if I wanted to find x-intercept or septs. Okay. Now, obviously, the origin is also on the x-axis, so we have found an x-intercept. But functions are allowed to cross the x-axis more than once, so there could be another. So I simply set the function equal to 0. So I would say, when is x squared plus 2x equal to 0? I can factor. X times x plus 2 is 0. So either x is 0 or x is negative 2. So I would have two x-intercepts. Those are going to be the x values that I just got, and the y value is 0. So I could also plot this other point here, negative 2, 0. Okay, next thing I've got, one thing about finding the intercepts. As you're doing the homework, read the directions. Okay, some problems are going to ask you to find the intercepts, some aren't. And generally speaking, when they don't ask you to find the intercepts, it's because you end up having to solve an equation that's very, very difficult to solve. Okay, so you might or might not be asked to find the intercepts. Just pay attention to the directions. Some functions will ask you for all of this. Some will just ask you for some of them. Okay. All right, symmetry and periodicity. Let's address periodicity first. A function is periodic, so f of x is periodic if f of x plus p is the same as f of x for some number p. Classic example of this is the trig functions. Okay, with sine, p is the period is 2 pi. If I take sine of something plus 2 pi, I get exactly the same thing as sine of that thing. Okay. So when I'm graphing a function that is periodic, I know I can just graph one period and then just sort of use arrows to indicate that that continues. Okay. Really, the only periodic functions that we're going to encounter this semester will be trig functions. That's not to say that other functions can't be periodic, just that that's not what we're studying here. Okay. Symmetry, though, a lot of functions do have some type of symmetry. So I want to remind you, we say f of x is an even function if f of the opposite of x is the same as f of x. So basically, opposite input yields the same output. Now we call those even functions because a classic example would be any even power function. If I take y equals x squared, if I plug in 2 or negative 2, I get exactly the same thing. When you look at the graph of an even function, you can see that the left-hand side is just a mirror image of the right-hand side. So we would say that this is symmetric about the y-axis. Okay. How do I check for whether a function is even? Well, actually, it's the same test for whether it's odd as well. So let me go over odd first, and then we'll review the test. I would say f of x is odd if f of the opposite of x is the opposite of f of x. So that would be opposite input giving me the opposite output. We call those odd functions, largely because a classic example would be any odd power function, y equals x cubed. So if I take 2 and negative 2 and I cube them, I get exactly the opposite response. When we have something like this, we have rotational symmetry or symmetry about the origin. Rotational symmetry, just because if I flipped this upside down, it would look exactly the same. We also call it symmetry about the origin, because it's like if there's a point here, x, y, it's like if it looked in a mirror at the origin, it would see its mirror image over here, negative x, negative y. So if I have either of these types of symmetry, then I kind of know, if I know one side of the graph, I know what the other side of the graph looks like. So that can be a nice shortcut when I have that. Okay. Now there are a lot of functions we're going to work with that pretty clearly don't have any sort of symmetry. So again, read the directions for whether you're asked to check for this or not. But let's suppose that we were asked to check for symmetry. So let's say I had f of x equals x to the fourth plus cosine of x. And I'm asked, is this even, odd, or neither? Well, the way I check is I simply plug in the opposite input. So I'd say that would mean I'm taking the opposite of x to the fourth power plus cosine of the opposite of x. Now, when I take a fourth power, that just kills off that negative sign, and cosine is an even function. If you don't remember that, take a look at the graph of cosine. It's got that symmetry about the origin. So notice that's exactly the same as f of x, so this function would be an even function. So that's how you check. You simply plug in the opposite of x and simplify. If you get exactly the same thing as f of x, you have an even function. If you get exactly the opposite, you have an odd function. If you don't get exactly the same thing or exactly the opposite, then it's neither. Okay. Holes in the graph. That could be something like, let's suppose I have f of x equals e to the x times x over x. Okay. Well, pretty clearly, because 0 would make the denominator 0, 0 is not in the domain. But I can see I've got a factor of x on the top as well. So this function is equivalent to e to the x with the restriction that x can't be 0. So what I would do is I would simply graph e to the x. Now I know e to the x at 0 would have a point at 1. I'm going to remove that point and replace it with a hole. So there would be a hole in the graph at 0, 1. So anytime you have a situation like this where you can cancel a factor from the top and bottom, and that whatever would make that factor 0 is not in the domain of the function, but if it's in the domain of what you would get if you canceled, and you just have to sort of record that restriction separately, then you simply have a hole in the graph. And the location of the hole is exactly where you would have a point if you didn't have this restriction. Okay, so that's a good start for us. I do want to talk about asymptotes. That's what we'll pick up with in the next video. See you soon.